We have already seen how QuickSort works. In this lesson, we do the analysis of QuickSort, both its worst case and average case time complexity, and then we will also look at an iterative version of QuickSort which eliminates the recursive calls. So, as we know, QuickSort is a divide and conquer algorithm. If the input is not small, then it calls the partition algorithm and then calls itself recursively for the left partition and the right partition. And the partition algorithm, as we know, in the in-place version starts with two pointers I and j at the two ends of the array, and it starts moving them closer to one another. I moves to the right, j moves to the left. Along the way, if it finds any element in the left which belongs in the right partition and any element on the right which belongs in the left partition, it swaps them, exchanges them. So it is doing both comparison and swap operations, but it turns out that there are far more comparison operations than swap operations, or at least the number of swap operations cannot be greater than the number of comparison operations. So we are going to only count the comparison operations. So if we consider the worst case of QuickSort, as we already talked about it in the previous lesson, that happens when we don't get equal partitions. So the true worst case is every time partition is called, it gives us highly skewed or the most unequal kind of partitions. For example, the first call to partition might give us only one element in the left partition and n-1 in the right partition. The next call to partition for n-1 elements might give us only one element in the left and n-2 elements in the right, and so on. And when this happens, the recurrence relation for the time complexity of the worst case of QuickSort will become T of n is T of 1 plus T of n-1 plus the cost of partitioning. Right? So what is the cost of partitioning? That is of n comparisons, right? So there can only be n comparisons that are made when partition is called for n elements, and therefore we count that in the recurrence relation. So T of n is T of 1 plus T of n-1 plus n. Now if we substitute n-1 in the same formula and apply the substitution method for solving this recurrence relation, T of n-1 becomes T of 1 plus T of n-2 plus n-1, right? And the T of 1 and n remain the same. So if we keep on doing this, we get n times T of 1 plus the summation n plus n-1 plus n-2 down to 1. And as we know, this summation is nothing but n into n plus 1 by 2, and this will be T of 1 is some constant, n times a constant plus n into n plus 1 by 2. So this term is of the order n square. So we can say that the worst case complexity T of n of QuickSort is order n square. Right? So that is why, because of these unequal partitions, we do not get n log n, we get n squared as the worst case complexity of QuickSort.
Its average case performance is very good, and that is what matters in practice a lot of times when we actually use QuickSort as the sorting algorithm in an implementation. So to analyze the average case complexity, we need to make a few assumptions. As always, we only count comparisons. Other operations such as swapping and so on will be of the same order or of a lower order than the number of comparisons done, so we only count the number of comparisons. We also need to make two other assumptions. We assume that the data elements are all distinct, that is, no two data elements are equal to one another. We also assume that the partition occurs at a given position with equal probability. That is, the probability of the partition occurring in position 1, that is the first element of the data being the pivot, is the same as the probability of any ith element becoming the pivot, right? So the partition may occur anywhere along the data array with equal probability, and using that We analyze the average case because the average case performance is very significant in actual practice, and it turns out that the average case of QuickSort is much faster than its worst case. So the average case is not going to be n squared. Right? So now, how do we analyze this? When we do a partition, we get two sub-problems. One is of size k minus 1, the other is of size n minus k. The other extra element will be the pivot, which is actually in its correct position, so it won't belong to either of these sub-problems. For various values of k, which occur with equal probability, we have to write the recurrence relation. Let's say we write t sub a n to indicate that it's the average case. It will be n plus 1 plus 1 by n times the summation of 1 less than or equal to k less than or equal to n of Ta of k minus 1 plus Ta of n minus k. How do we get this? This is the cost of solving the first subproblem. This is the cost of solving the second subproblem. And those subproblems for various values of k occur with equal probability 1 by n. Hence the summation. Right? And then this is the cost of the initial partition. When we do the initial partition of n elements, we do n plus 1 comparisons. Right? That happens before any of the subproblems are generated. So that is also included. To analyze this, we have to do a lot of maths. Right? We are going to multiply both sides of this by n to get rid of that 1 by n. If you do that, we get n times Ta of n is equal to n into n plus 1 plus 2 times of Ta of 0 plus Ta of 1 plus etc. Ta of n minus 1. How did we get this? Because these numbers are all symmetrical. When you consider all the values of k from 1 to n, you will get t of 0 twice, t of a twice, and so on. Right? Now, we replace n by n minus 1 in this equation. So, you get n minus 1 times Ta of n minus 1 is equal to n into n minus 1 plus 2 times of Ta of 0 plus Ta of 1 plus etc. up to Ta of n minus 2. Now we subtract this from this. Right? So when we subtract those two, we get n times Ta of n minus n minus 1 times Ta of n minus 1 is equal to 2n plus 2 times Ta of n minus 1. Right? I'm going to rewrite that on the next slide. So we got n times Ta of n minus n minus 1 times Ta of n minus 1 is equal to 2n plus 2 times Ta of n minus 1. This can be rewritten as Ta of n divided by n plus 1 is equal to Ta of n minus 1 by n plus 2 by n plus 1. Right? Now we repeatedly substitute this to obtain Ta of n minus 1, Ta of n minus 2, and so on. Right? If we do that, in the end, we can arrive at Ta of n divided by n plus 1 is equal to 2 times sigma 3 less than or equal to k less than or equal to n plus 1 by k. Right? That's the summation we arrive at. Now we are going to analyze this particular summation. Let me do that on the next slide. So we had Ta of n divided by n plus 1 equal to 2 times sigma 3 less than or equal to k less than or equal to n plus 1 of 1 by k. Now this particular element, right, is less than or equal to integral 2 to n plus 1 of 1 by x dx, and that happens to be log to the base e of n plus 1 minus log to the base e of 2. And from that we can now say Ta of n is less than or equal to 2 into n plus 1 into this whole thing, log to the base e of n plus 2 minus log to the base e of 2, right? So which is O of n log n. So here is a log n and n. So this order of this is O n log n. So the important thing is the average case performance of QuickSort is n log n. Its worst case is n squared. But what really matters in practice is average case. Can we make further improvements on QuickSort? We can eliminate recursive calls to QuickSort by using an iterative version, but doing so requires a stack, right? And its size of the stack should be of the order of 2 times log n and so on. So what we do here is we have an outer loop that is repeated forever until false. So it only exits when we do this return from the inner loop. In the inner loop, as always, if we see if the problem is trivial, low less than high means there is more than one data element, the problem is not trivial. So as before, we call the partition algorithm to obtain j. Now we compare the two partitions that we get, right? So here is one partition, there is j for you, this is low, this is high. So I'm comparing j minus low, that means the length of this, with high minus j, which is the length of this. If the first partition is smaller, if j minus low is less than high minus j, then we sort the first partition first, and we remember to sort the second partition. How do we remember to sort the second partition? We push j plus 1 and high to onto the stack, and we set high to j minus 1. That means we solve the first part first. Otherwise, if the second partition is smaller, we solve that first. We set low to j plus 1 and solve the second partition first, and we remember to solve the first partition by pushing it onto the stack. In the end, when the stack is empty, we return, and when we are done with one partition, we delete those two values. So by using this stack, the iterative version does not make any recursive calls, and it also always solves the smaller partition first, and doing that gives us even better performance. You can look at some of the performance numbers given in your textbook. You will see that often the performance of QuickSort is twice as fast as that of merge sort in the average case. So QuickSort, as the name suggests, is a highly efficient divide and conquer algorithm, although in the worst case its performance can be of order n square. So when does the worst case occur for QuickSort? With our assumption that the first element of the array is the pivot. Does it occur when the data is already sorted? Does it occur when all the data elements are equal to one another, or no two data elements are equal, or when some of the data elements are equal to 0? When does the worst case occur for QuickSort? The correct answer is A. When the data is fully sorted or almost sorted. That is the worst case for QuickSort, because what happens is each time the first element will be the pivot. So you will end up with those n minus 1 kind of partitions. So it will have to go through n minus 1 recursive levels, not the log n kind of performance that we get by dividing the array into two roughly equal parts. So because of that, the worst case for QuickSort is when the data is already sorted. That gives the n square kind of performance. Thank you.